Okay, very good afternoon, or good evening, depends on the season, I guess. Assalamualaikum. Ni hao ma. Konnichiwa. Bonnicum. Or so far, all the speakers have thanked the organizers for organizing this, but I think let me special thank to the audience today, which is the students, you guys themselves, because I think you guys are spending your weekend in this great hall, listening to like 5 to 6 hours of lecture. Amazing, unbelievable. Okay, that reminds me actually that I used to have classes from 5 to 6:30. In the evening, where half of my students are basically sleep, or the other half pretending to listen. But you guys are still, after the lunch, still here. Amazing, amazing. My presentation today, or not really a presentation, more like a sharing session, is more on the fundamentals of jet engine and the roles of turbulence flow in aerospace propulsion. Basically that I'm be focusing more on the basics of the jet engine, if you are interested in, okay? As well as, because jet engine basically they work in a high-speed flow. Okay, so we are dealing with the supersonic or turbulence. Anyone knows what is basically turbulence flow? What is actually turbulence? Turbulence, they have many, by the way, that are definitions, but basically turbulence is we are dealing with the instability, or unstable, or stability. So what is actually instability? How do we describe instability? Anyone knows? If you have a pendulum, okay, if you don't have, just pretend this is a pendulum, a name tag. Is this a stable configuration or unstable? It's not moving, right? It's a very stable configuration. Now you move into this particular configuration. What happened then? It moves back into the stable position. The same thing here. I put like this. If move back to the stable position. So everything do not like unstable, being unstable. Okay? The same thing, for example, if you have raindrops, which are water in air. Raindrops, right? Raining. Water in air. Compared to, you have a bubble, which is gas in water. Which one is more stable, by the way? I repeat, the raindrops is water in air, or a gas bubble, which is gas in water. Raindrops from the clouds until it reach the surface, survive. Right, very stable. But gas bubble is just a few seconds. If you go diving, your oxygen, a few seconds. Very unstable. So everything's involved unstable. Imagine if you have a jet engine, high-speed flow. If you have rotating equipments, turbines, compressors, okay, supersonic conditions. It is extremely difficult measures, okay, difficult engineering applications. But I'm not going to scare you of those highly mathematical equations and so on. And also that I'm not going to argue whether that mining or mechanical is more important. So I'm here basically, as I said, to share some of the important information. In order to appreciate the applications, you really need to understand what is the history behind it. Just going through some of them. The basics of the propulsion, the jet engine, then how we can increase thrust, for example, for the supersonic, the military aircraft, or even the Concorde, okay? And what happened that if you have a supersonic conditions, then you have a shock waves, okay? That will impact the performance of the jet engine, the inlet components, and so on. And last but not least, the brief introduction on the rocket engine. As I said, I think a few days back, or not, maybe last week, I think, there was an incident about the Ethiopian airline, okay? 737, Boeing 737 MAX. Anyone knows what happened? Nobody knows, right? Nobody knows. But in fact, there was the second time, Boeing 737 MAX, okay? The second time within 5 months. Nobody knows. It can be the human errors. It can be the maintenance issue. But 737 MAX is a pretty new aircraft, okay? 2016, 2017. The latest series in Boeing 737. Or it could be the, I don't know, maybe propulsion problem. Or it could be the software, the control system, okay? No one knows. But the thing is, basically, that pretty sure is the aircraft doesn't have enough propulsion to fly forward. Simple as that, okay? That's why the nosedive and crash, okay? But it's not an easy question to be answered. If I know the answer, I'll be rich by now, by the way, so I do not know. So in fact, it's a very difficult problems. So we need to understand what's behind it, what's behind the jet engine, the principle, okay? The fundamentals behind it, how can actually that we created work from the, because jet engine has many components. It has inlet, it has compressors, combustors, turbine, and of course nozzle. In some cases, for example, Concorde, you have the afterburners. Okay, so many things happen. As I said, we need to appreciate the history. A little bit, I know history is a bit boring, by the way, but okay. I think our governments do realize that there's a potential of speed. Okay, there's a potential of speed in turbojet engine. That's why that in war, in any wars, you need to be very quick. Okay, you need to be fast, at least faster than your enemies. Okay, so that you can what? Intercept the missiles, for example. Okay, the first one can go into the front lines. So the Glossier Meteor was the 1943s, actually used engine by Rolls-Royce Welland turbojet, is the only aircraft used by the Allied forces for military advantage. That's why that perhaps that the speed bring the advantage to the Allied forces during the World War II. Then the post-war, 1950s, for example, there's a growing growth in the commercial jet engine. Then we have in North America, for example, the GE, General Electrics, or even the Pratt and Whitney. They started to dominate the jet engine market. Okay, they use the same engine for the military and also for the commercial airlines. Then we have the Avon. Okay, the Avon is basically the first Rolls-Royce engine, the first one that used the cool high-pressure turbine blades, axial compressor, basically that to generate more thrust. Britain's first supersonic fighter, 1950s, the first Britain supersonic fighter. Supersonic here means that Mach number is more than 1. Okay, Mach number is more than 1. Mostly the commercial airlines is less than sonic, around 0.8 or 0.9. Okay. Then we have the Conway, again developed by Rolls-Royce. Conway is basically that twice faster, twice more thrust, okay, compared to the Avon, the previously one. Then used by the Douglas DC-8 and also Boeing 707, the world's first bypass engine. What does it mean by the bypass engine? Bypass means that it's more like a turbofan. Some of the air is not being combusted, it's not being compressed, it's not being used for the work. Some of the air is just basically used to bypass these components to cool down the turbine blades so that more combustion can be raised, more power can be generated by that particular engine. So we have this Lockheed TriStar, Boeing 747. They use a very large turbofan, titanium fan blades, and so on, because titanium fan blades are very high resistant to temperature. You can see here the growth of the thrust for the commercial and also for the military aircraft, and also here, you can see that the growth of the turbine entry temperature. Okay, turbine entry simply is this: if you have high temperature, meaning that you can You can add more heat, more combustion properties, more power generated, more thrust. Okay, so basically the developments for the jet engine, agents for change. We have a new materials, titaniums or ceramics because of their high resistance for the heat. and also the advancements for the CAD and CM, computer-aided design, computer-aided manufacturing. Basically, all this process, we can save time, okay? Basically, the designing, all the design process, very easy for us to alter, to modify it before we commit into production, all right? And also the advancements of FEA, finite element analysis, and also CFD, computational fluid dynamics. All of these basically we can use for simulate the stresses, okay? Flow analysis is very cheap, by the way, in terms of the physical resources. Rather than we to have a very large wind tunnel, physical tools, very easy for us now to advance the knowledge on the particular area. I think you guys need to smile a bit, I guess. You guys are too serious, by the way. Very, very serious. I know that this is a late afternoon, but you have to enjoy the moment, okay? Enjoy the moment. It's not easy for, I mean, that this is a very historical moment, by the way, so smile a bit, all right? The other applications we have, like, even in power plants, okay? Helicopters, in marine engines, even in oil and gas applications, in aerospace, rocket science. So these requires knowledge on the propulsion, okay? And also the supersonic condition. As I said before, aerospace exploration is it's a very dangerous, by the way, and risky. It's very, very dangerous, especially in the case of the rockets, okay? Especially in the case of the rockets. Why? Why, for example, how big is the rocket? I mean, the space shuttle, how big is that? It's huge, right? Why it's huge? Because it needs to carry people. It needs to carry equipments. Satellite, for example. It needs to carry what? Their own oxidizer, the oxygen. Why? Because there's no oxygen out there. So they need to carry huge gas tanks, plus the propellant. They need to carry every single thing, okay? That's why the instability in the rockets, for example, can cause lots of problems. For example, 1986, I'm not sure whether that you were born or not, but I'm very sure that I'm less than 10 years old during that time. 1986, Challenger crash. Challenger shuttle crash, okay, because of the propulsion, the leaking, okay, killing all people, all astronauts, 7 people died during that particular day. Then we have the Columbia shuttle, 2003, Columbia shuttle, during the re-entry, disintegrated because of the high temperature, thousands of degrees Celsius. The material couldn't withstand, killing again all the astronauts, okay? And many other incidents as well. Even the Air France, okay, Concorde. What else? 477 Air France, I think during the year of 2006 or 2009, if not mistaken, somewhere between the Brazil and Paris, okay? Again, crashed along the Atlantic Ocean. Now I go into a bit of the theory. But I hope that you can bear with me. But it's very easy, by the way, in terms of I'm not going into some of the heavy mathematics in order to appreciate this. But basically, propulsion is all on the Newton's third law. We have 3 laws, right, Newton's? First law, second law, and third law. The inertia, the momentum. The third law is basically, for every action, there is an equal or opposite reaction. So the idea is to create what? To create the action. How do you create the action? Action means forces, the thrust. How can you create thrust, for example? Okay? So the thrust is basically differential equations of the mv over time. But again, I'm not going to go into details of this. But at the end of it, you would have the force is basically the mass flow rate times the velocity times the difference in the pressure. So the keyword is m dot and v, the mass flow rate and the VE. VE is what? The exit velocity. The exit velocity of the nozzle. So meaning then, if you can have a very high velocity exiting from the nozzle, then is a big thrust generated. So how can you create more velocity outside the nozzle? It's a very difficult thing. That's why that you need to combust, you need to compress the air, okay, combusted into very high temperature because the velocity depends on the temperature, okay, and many other things. And other some important parameters. I'm not going into this in details. I will skip this. But basically, these are the basics of the jet engine. As you're probably aware, we have the inlet here, is basically where the air comes in, okay, drawn into the, or decelerated because you have the converging and diverging nozzle. Decelerated so that it can go into the compressor at a very lower speed. And then we compress the air, okay, make ready for the combustion. We combust it. And then we have the turbine expanded so that this can the turbine can be rotated by the action of the mechanical work. In some cases, you have the afterburners. In some cases, after the turbine, there are some leftovers of the oxygen that can be added into fuel. You have more combustion. And then temperature rise again, and then the exit velocity can be increased. Simple as that. In some cases, in high-speed application, you don't really have mechanical equipments. You don't have a compressor. You don't have a turbine. How it works then? In which application? Imagine your jet engine doesn't have a compressor, doesn't have a turbine. Simply just the air is being sucked into the jet engine through inlet and then combust. How that is possible then? Is it amazing? This is only can be done if you have a highly supersonic flow, hypersonic for example, where if you have a very high speed flow, the compressibility is increased. So the air is basically compressed by itself. The design of the jet engine actually that allowed this compression to take place, even without the physical compressor itself. Okay, amazing. Then you inject the fuel, ignited by itself. Okay, but people might ask, how can this aircraft work? Because in order to achieve a supersonic or hypersonic, you need to start from zero, right? How can this aircraft suddenly flowing at Mach number 5? At this moment, this particular aircraft or this particular jet engine is being attached to a bigger jet engine. So at that particular speed, this aircraft can be released a smaller scale, okay, can be released and then operating at a high supersonic at the instant basis. All right. You have Concorde. Concorde is flying what? Mach number 2, Mach number 3. Amazing during that time. Okay, but Concorde is extremely expensive to operate. Okay, also have a sonic boom. Is by regulations, the noise is not that comfortable to people. I think it was ceased to operate. I think around the year of 2000 because a major accident. Concorde on the year of 2000 from Paris to New York City. Okay, during the takeoff, something happened, hit some mechanical things, leaked the fuel system, and after that burst into flames and crashed, killing all people again. So these are, as I said, Concorde or military aircraft, the supersonic jet, they have the afterburners. They have the afterburners application. Again, as I said, the velocity is depending on the temperature. You increase the temperature as high as possible. But again, as I said, what is the limitation? Is the properties of the turbine blades. Yes, you can increase, you can add more heat. You can increase the temperature, the combustion capabilities. Again, the limitation in terms of the material. These show that if you increase the temperature, then the energies of the flow increase. Okay. I'm not going into these mathematical details. Do not worry. But just my argument is, what happened then if you have afterburners? This affects the performance of the jet engine in terms of the extra thrust, in terms of the fuel consumption. Okay, fuel consumption. That's why in this graph it shows that with and without the afterburners. As you can see, 50% to 100% gain more thrust, but with the side effects of the fuel consumptions. That's why that passenger airlines such as Concorde is very expensive to operate, but luckily for the military aircraft, they operate on a supersonic basis on, not every time, that's in a certain situation, okay? Then we have the scramjet propulsions, as I said before, at a very hypersonic flow, no mechanical equipments again, just all the nozzles and converging, diverging nozzle. But the issue is, I know sometimes maybe this is beyond the knowledge in this particular level, but in case that you are interested, at the moment you introduce the supersonic flow, then there is a shock waves, okay? I think you're familiar with the word sonic boom, okay? When the aircraft flying very close to you, there's like a boom sound, okay? This basically, the boom sound is due to the generation of the shock waves. It's a very tiny layers, but the difference in the properties are significant, downstream and upstream of the shock waves. The pressure densities, the pressure properties, the densities, the temperatures are increasing very, very highly, okay? So this would affect, for example, the performance of the compressor. That's one of the reasons actually, the Air France 477, during that particular night, when they flew from Brazil, Rio de Janeiro to Paris, somewhere along the Atlantic Ocean, okay, the pitot tube gave an error. The pitot tube gave an error, okay? Pitot tube is basically that to measure the airspeed. And by the Bernoulli equation, the airspeed can be converted into I think the other way around. The altitude, okay, can be converted into, the speed and altitude can be related. So something happened in the pitot tube. The pilots do not know the speed of the aircraft and did not know the height of the aircraft, the altitude, okay? And the flight flying in the middle of the night. So basically then afterwards, things happen in sequence and after that crash. So basically the pressure performance, depending on the properties, the turbulence properties. At the moment you have a shock waves, the properties of the pressure varies. The stagnation properties, the mean properties, and also the turbulence properties. So basically this will affect the performance of the compressors, the inlet, And these are due to the changes in the acceleration and altitude, free stream turbulence, whether you have a calm flow or variations in the winds, the angles of attack, for example, if they have any turbulence, the clouds during the takeoff, during the landing. So this all affects the performance of the jet engine, okay? That needs to be taken into consideration. This, as I said before, in contrast to the jet engine, the rockets, they need to bring everything by themselves. The oxidizer, the propellant can be in terms of liquid or can be in terms of the solid. They need to carry on top of the existing payload, the people, equipment, satellites, and so on. So the application is a bit more complex and a bit dangerous. So basically, the nozzle converts the thermal energy into the kinetic energy for the rocket applications. That's why that if you notice then, actually the space shuttle is not that big, but the booster is really the one that takes all the space, okay? That's why that I think if you notice SpaceX, the Tesla companies, they try to develop where the boosters can return back to the station. Well, Falcon Heavy is still under the research investigation, but it's very amazing and also that difficult to do. But somehow they manage, maybe around 60 or 70%, they manage to do that. Again, the aerospace propulsion is a very complex matter. It involves many components, either in fluid compressible flow, shock waves, chemistry, the combustion effects, the fuel itself, structural or the aerospace structures, the plasma formation as described by previous professor, thermodynamics and heat transfer mechanics, quantum mechanics, and also nuclear physics. Okay, So basically, depending on applications, depending on whether that at what Mach number that you are operating the aircraft, so basically that determines the types of the jet engine that you require. Either the propellers, the turbo propellers, what else? Either the turbojet, either the turbofan, or even the ramjet and scramjet. Depends on types of application, but still something that any mechanical engineers, I believe, is something that could interest you. All right? That's it. Okay? With that, I end my presentation. I believe that Q&A will be